the whole process.
Okay.
So, for those of you just tuning in,
Welcome.
yeah, Rob messed up.
We were talking for the last couple minutes, but we can redo that. It's okay. So welcome to season 3, episode 8 of the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse.
And I'm Robert Moore, the mess up. So
we are broadcasting.
I'm Dean Smith.
Yeah, Dean's our special guest today, but we are broadcasting live from the university, and you can tell it's live from the University of North Dakota here in Grand Forks, North Dakota. So we're happy to have Dean with us today. But like always, first of all, a disclaimer: anything that Rob and I say, or even our guests when we have them, sometimes we do, it's our own personal opinions and not necessarily those of the university or anyone affiliated with the university or anybody else. It's just our own personal opinions, so you know who to blame. Now, the other thing to mention is we do have a live chat feature that's running. If you have any questions or comments related to what we're talking about, we would love to see that. If you have something that's unrelated to what we're talking about, completely off the wall, and you're not looking for any comments or feedback, just send those to us in an email.
Great.
How's that?
That sounds good.
Now, what we're going to do is we'll start off by having Dean talk to us about the sky and what's going on in the sky at this moment, the spring sky. We're getting very, very close to spring, which is always nice to see this time of the year.
Oh, yeah.
We can't wait till spring. And then if we have time after that, then we'll kind of update people on some of the astronomy news that's going on. So, Dean, take it away.
All right. So I think I'll share my screen.
Okay.
So everybody can see what I'm talking about.
And now they see you.
They see me. Let's see if I can figure out Zoom again. All right, so this is the sky tonight. I put it at about 7:30. So this is stellarium. I've used this before. If you've seen me before on here. And one of the things that's been in the news is this planetary alignment. And I do feel like I should mention that planets are usually in a line. That line actually has a name. It's called the ecliptic. And this line here is the ecliptic. And that's just because the solar system is flat, right? All the planets kind of orbit the sun in a plane. So the fact that they're in a line isn't really different. They're always in a line, but there's quite a few of them that we can see. Oftentimes some of the planets are on the other side of the sun, right? We can't see them all. Even now, even though they're technically a bunch of them that you can see, some of them are going to be really difficult, like Mercury and Saturn. You're going to have a rough time. They're going to be low in the west. And even at 7:30 here, we can see Venus. Venus is very bright, easy to see. But Mercury, you got to go to about 6:30, and then you got a lot of the sun there. So it's going to be a challenge. So if you go out at 7:30 or 8, Mercury and Saturn are probably going to be hard to see. But Venus is going to be out bright, low in the west. What's interesting, Venus will show a phase, and right now it's really thin. If you go out and you look at Venus, and it's so bright, you might think, well, that must be like a full phase, like the full moon. It's actually a thin crescent right now. When Venus is a gibbous phase, so more than half full, it's further away. It's on the other side of the sun, right? So because it's further away, it'll be dimmer. So it's kind of interesting that when you go out and look at Venus, it's very bright. It's brighter than Jupiter. It's this little crescent right now, and you can see this in a telescope. So if you have a telescope, you can point that at Venus and see this crescent phase. So,
I'm going to interject and point out that actually you don't even need a telescope. If you've got a good zoom lens on a camera or a pair of binoculars, you can see this. So, Venus is a nice target because it is good and bright.
Yeah. And only Venus and Mercury are going to show a crescent phase. The other planets further out, they will show phases, but they'll always be gibbous. So, and then obviously the moon's going to change. It's not always going to be in that spot, but tonight, moon's kind of the next one up. And I might zoom in on that just to point out, I don't normally talk about Mare Crisium, but that is where we just had a lander land on the moon. So, and so that is a feature that you can see pretty easily in a small telescope or binoculars. And so, and I think you'll be talking about that later in the news section. So, but that's actually where we just had something land a couple days ago on the moon.
Now, Dean, I can interrupt for a second. That also demonstrates that where this lander essentially runs on solar panels, solar energy, that it needs the sun above the horizon, that you can tell from that location of the moon that it's got several days to go before the sun starts setting.
Right.
Right. Yeah, and they're trying, I think they're trying to have a full lunar day, so it's 2 weeks
Yeah.
of sunlight. And so they landed there when this was even a smaller crescent, right? When we just started to get daylight there. And so
Right.
they're going to try and have that full 2 weeks so of daylight.
Nice. Excellent.
And then we got Jupiter, bright, pretty easy to see. And if you go out, we look at the directions here, you can see Jupiter a little west of southwest, so at 7:30. So you don't, early in the evening you can go out and catch Jupiter. Jupiter, you look at it in like 10 power binoculars, you can see some of the moons. The challenge usually is they get lost in the glare of Jupiter. So, but you can see the moons of Jupiter. Small telescope, you can see a couple cloud belts. And there's a moon shadow tonight. If you got a small telescope and you go out, you might see a shadow of one of the moons. That happens every once in a while. And it is visible, to the eye if you have good seeing, if the conditions are good. You'll see a black spot on Jupiter. So
Now, Dean, do you have a time roughly when that occurs tonight?
yeah, I think I have this set for 7:30. Yeah.
Mm-hmm.
And I'll admit I didn't look too much at this. Is there another one that pops up? Maybe not. So, yeah.
So it's Ganny, Europa, and Callisto that are the three Galileans.
Yeah, on the
that are
right
visible.
side. I'm guessing Io must be behind it.
Yeah.
So, oh, there's the second one. So if you get out early, it's still kind of twilight. We can see the background brightening up.
Mhm.
There is around 6:30 two shadows at the same time.
Excellent.
So, but you'd have to get out. There's still a little twilight out. Catch that quick, that one there. So, and I'm guessing this is Europa and Ganymede casting the shadows.
Mhm.
So,
As soon as we're done the podcast, we got to run, Robert.
yeah,
Oh,
right.
at
This is
right.
So you
basically,
have to immediately
it's going to be
go.
like right after, and it's cloudy, isn't it? So,
Yeah.
Oh, okay, now we can crawl.
so it won't matter anyway. But
Oh
yeah,
man.
so, but yeah, if it's clear where you are, that's an interesting thing. And I have seen two shadows, even taken pictures of two shadows. So, so that happens every once in a while on Jupiter. It's a neat thing. And
The
then
other-
Mars. Now,
Sorry, can I interrupt again? So, Dean, you've used this program a lot, in past podcasts, and great for illustration purposes. Can you say a word or two to those who may be interested in acquiring this and running it on their computers?
oh yeah, so yeah, so this is a Stellarium. It's free if you go to stellarium.org. I'll drag a browser over here. It runs on Linux, Windows, Mac. There's a web version. If I could type. I get okay. Well, there's a web version somewhere. I
Nice.
thought, click this link.
There you go.
Then you
That
don't
makes
have
it easier.
Stellarium-web.
That's for in the middle of the
So-
night when you're trying to observe something and you're half
Yeah.
asleep.
So you can click the link and it'll go there as well. There are some features the last time I checked that are missing. But generally this will work fine. If you just want to know what's up tonight, right? This is the web version, and it looks a little bit different. But pretty similar. I can have stellarium on top of stellarium. The keyboard shortcuts are different. So,
Now,
um,
if you wanted to know, for example, if you have a telescope and you wanted to know when is the red spot of Jupiter sort of in the middle of Jupiter, so I can go out and have a look at it. You can use this to go in time, either backwards or I guess forwards is where you want to go, to try to see when that spot appears, right? And
all
then
right.
you know when to go out.
Yeah. And so if I zoom in on this, and zoom in more, this is just the mouse wheel I'm using. I can animate down on the bottom here. The menus are kind of hidden, yet bring your mouse down, a little menu pops up. And if I click this, you can start to watch it kind of turn. And we can just kind of wait. Oh, there's Io just came out of the Jupiter shadow, so that's interesting. And maybe the red spot will pop up tonight.
At some point, it'll be there. It's like what, a 10-hour orbital period?
Yeah,
or
it takes 10 hours, so
rotation, yeah.
oopsie.
Whoa.
Oh, I think it just went below the ground.
Oh,
Oh,
okay.
maybe not then.
Oh,
So-
it went behind this tree, which
Chop that sucker
you may or may
down.
not have a tree, but yeah.
As
And I can actually
Washington,
get,
as Washington said about the cherry trees.
there we go.
All right.
We'll just get rid of the ground. We can do that, and so but yeah. So
There it
so
is.
it comes up about 12:30 to
12:30.
1, probably about 1 a.m. go out.
And
so
that's still above the western horizon.
yeah, it's starting to get low.
Okay.
But
I mean,
somewhere in here, the altitude's 13 degrees, so
Yeah, it's fairly.
it's
Yeah.
getting low then. So, but yeah, that's when you can find the red spot. You can identify the moons. So
You just got to wait, a week or two, and then it'll be there at the point where you go out to observe at a good time, anyways, right?
Right.
Because
Right.
of that difference, 10 hours versus our 24.
Cool.
Nice.
I like
so
stellarium.
yeah, and I recommend this to people. It's free, fairly easy to use.
I like the free word.
Free word.
Yeah.
And I will
So-
point out that it's if you're interested in the constellations, Jupiter is right near bright star in Taurus, Aldebaran.
Right.
Which-
That's this one right here.
So the Eye of the Bull, as it's called. So that's another thing to look for right around Jupiter is this reddish star
So
called
there's the eye of the
Aldebaran.
bull.
There's the Eye of the Bull.
And of course, Mars is in Gemini.
Yeah, so we got Mars here. And you could confuse these. Aldebaran is a red star. Mars is a red star. So right now Mars is brighter. Now Mars was at its best in January. I went out in late December when we happened to have a 30-degree night and did look at Mars, and it looks nice. It looked nice. Now we're kind of past its time to shine. So usually you have 2 or 3 months where Mars is good. We're kind of getting past that point. So it's still a nice bright red star in the sky, but in a telescope has gotten pretty small, and it's difficult to see the features on it. So, and we can see it's already in a gibbous phase. So when it starts to show this gibbous phase, we've kind of left it behind. So Earth is going faster in its orbit. We're kind of leaving Mars behind. It's getting smaller and smaller in the sky. So, but usually when we're at a close point, if the winter hemisphere is facing toward us, there's a tilt in the axis. You can see a polar cap. I did bring a picture that I took in December. Don't know where it went.
I'm sorry, I got hungry. I ate it.
Now,
Okay,
now
I'm just kidding.
stellarium that shows like the two polar caps, that's just illustration purposes only, right? They don't know what degree that the polar part of Mars is being covered at any moment in time. Is that true?
Right. Yeah. So they don't necessarily. Yeah. So this isn't a real-time image. It's a simulation.
Right.
So it will show. It will show the cap that is facing us. So if there's a tilt, right? So if the winter hemisphere is facing us, it will show that polar cap. And so you can see which one is visible. So this is a picture that I took late December, I think December 28th. And here you can see the bright polar cap that was pretty easily visible in a telescope. So that doesn't always happen. Sometimes the summer hemisphere's toward us, and the polar cap in the summer is a lot smaller, and it's not as obvious, but this year the polar cap was pretty noticeable. You might see this little bright spot over there. It's not very easy to see, depending on how YouTube is showing this. That actually is a cloud over Olympus Mons. And so Olympus Mons is occasionally shows up in pictures. I've never seen it visually. It's really difficult. There are reports of it from the 1800s, so apparently this was a known feature back then. It was kind of a bright spot. It's usually really hard to even get a picture of, but it's easier if there's a cloud over it because it's bright. And so, I have a friend who has the same telescope as me who took a picture of it about a month later at the end of January. Happened to be the same part of Mars, and that same bright spot was there. So it was I don't know if the cloud was there for a month or came and went and came back again. Yeah, it's not always, you're not always lucky enough to kind of have a marker to be able to see
Olympus.
maybe not the actual volcano, but at least a cloud over the volcano. So
Now, a question about telescopes. So you mentioned the 1800s. So back in the 1800s, most people are probably, there's no amateur telescopes that someone could purchase for a reasonable amount of money, and you could make them your own, of course. This is probably the only way. But a lot of people were using, the ones who had access to the equipment, the large refracting telescopes. So don't they provide a much sharper view of planets like Mars compared to a similar telescope, let's say like a reflector?
yeah, if you have a long focal length,
Yes.
which a lot of them were then, a long focal length refractor, yeah, you can get a better view, assuming it's a high quality refractor.
Yeah.
Right.
With the aberrations kind of corrected. So typically, if you have the same aperture and focal length, a high quality refractor is going to be better than a reflector
Yeah, so
for the same cost.
Yeah, well, I'm thinking, people
It's different.
had noted these things, like you mentioned already from the 1800s, but I wonder if a lot of those reports are from people using what we would consider, professional type telescopes today with the big long refractors and the large f ratios. Right?
Yeah, I guess I did not look into what telescopes people were using that reported seeing it.
Right.
Yeah, I've never seen it visually, and it's obvious it's not easy to even get a picture of. So
Plus, you could have somebody observing from a place like, I don't know, Arizona,
Right.
yeah,
where the
you
seeing
do
is a lot
want
better.
you want Mars high in the sky and have good seeing.
Yeah.
So, yeah, and at close approach where it has a decent size in the sky. I know we looked at Mars last night, and it was tiny.
Right.
And I can say it was not as good of a view as it was in the end of December. That was a couple weeks from opposition.
Right.
And now I think we're like a month and a half away from opposition. So
Yeah, and you think of the relative speed, right? How long it takes Mars to go around its orbit once, and then the Earth, of course, is 1 year. So the approach and the receding speeds are quite rapid.
Right.
And
Yeah.
so it doesn't take much to really start changing it so it gets a lot smaller in angular size as you recede away from the planet, relatively
Yeah.
speaking.
yeah, we're moving away from it. And Mars is one you don't get to see every year. Like, Jupiter doesn't move very fast.
Right.
And so you basically wait a year for the Earth to go around the sun. It's like a year and 1 month. We meet up with Jupiter again. We wait a year, we get back to where we saw Mars. Well, now Mars has moved to the other side of the sun. And so then we have to go around again. And so it's usually every 2 years we get to see Mars. And that's also the launch window. So usually when NASA wants to send things to Mars, it's every 2 years you have that window to launch.
Yeah, and that's what's going to hit us when we go to explore Mars,
Yes.
humans. And
Right.
we can't just come back anytime we want because of the alignment of Mars and Earth would be such that it would be from the point of view of energy, if you want to think of it that way.
Prohibitive fuel.
Yeah, you won't be able to reach it. You have to wait for the alignment to be just right.
Right. You got to wait for our orbits to match up. And even like you want to send supplies, it's every 2 years. So,
Yeah.
you have that window. So yeah, that's a big challenge versus the moon where you can kind of, go whenever.
Yeah.
I'm trying to think of the early, like, I don't know, early 1700s, British exploring the South Pacific, but they could always land on Tahiti or something and get resupplied, right?
Right. Can't do that on Mars.
You can't do that.
Yeah.
Can't really even do that on the moon, But
No.
it's only a 3-day trip.
Yeah, 3.5 days or so, but
Yeah, and you don't have to wait too long if you want to send a resupply. So,
Right.
yeah, Mars, that's going to be a challenge. So,
yeah, I wonder if they'll ever 3D print a banana or something, right? That you could actually eat.
yeah, unfortunately, you can't 3D print food. It'll be made out of plastic probably. So,
And we have a question from Bill Schwalm. What are the things moving in the simulation? So apparently there were some things moving when you were
well,
zoomed
if you're
in.
looking at the red lines, that's just a crosshair from when I clicked on it. If that's what you're looking at, so basically anything I click on, there's a red crosshair that kind of moves in and out.
Right.
So
They may have been talking when you were zoomed in and were noticing something moving. I don't know.
And you can zoom in, and then when you have that crosshair on, that centers the object like Jupiter. So then when you go forward in time, Jupiter doesn't move out of the field of view, right?
Yeah.
Yeah.
So that's kind of the reason for that. Also, there's a shortcut zoom button, and so if I hit that button, it'll zoom in on the thing that I clicked on.
Okay.
So, and that's kind of why I do that. So I can hit a button and it'll zoom in. There we go, and center it.
Okay.
And then backslash will zoom back out again.
And then when you were zoomed in on Mars, you could see the two moons, right?
I think
Deimos
those are
and
two
Phobos.
stars.
Oh yeah. Oh, maybe that's
I thought this
yeah.
was,
So yeah,
Is that
we do
it?
have
Is that
Phobos
Deimos?
and
Okay.
Deimos there.
Yeah.
Yeah.
Okay.
You're probably not going to see those.
No.
I have tried. I've never been able to see these. Technically, they're within the range of a decent sized telescope, like a 12-inch telescope or more. But they're in this glare of Mars, which is so much brighter that I've never been able to see them. So
Now, speaking about glare, have you ever seen I know we're going off topic from planets, but have you ever seen the white dwarf companion star to Sirius, so Sirius B?
no, I think people have.
Yeah, that's for sure. I just wondered if you ever had a chance
Yeah,
to
I
see that.
haven't. It's actually one of those things. In the orbit, it's an elliptical orbit, so there are best times when there's the biggest separation.
Yeah.
Right.
And so, yeah, I mean, part of the problem is it's always winter, and when it's out.
From here, that
So-
is, if you happen to be listening in Florida.
So yeah, so I have not gone out and tried for, and for those who are wondering, Sirius is right down here. And it's pretty easy to find if you know Orion. You take Orion's belt, follow it down to Sirius, and this is the brightest star in the sky. That's not a planet, and it does have a white dwarf companion, which is technically possible for amateurs to see, but not easy. So
Right.
And you always recognize Sirius, that's the star people always see, catches their attention. Number one, it's so bright, the brightest star in the sky other than our own sun.
Right.
The other thing is that it twinkles a lot with the flashing colors because it's generally
Right.
low in the atmosphere from here.
Oh, right. Yeah.
yeah, stars that are lower in the sky tend to twinkle more, and that
Yeah.
one, people catch that
Yeah.
twinkling because it is so bright.
Yes.
Yeah. As long as we're talking about Orion, now that's technically a winter object, but you get out early in the evening, 7:30, 8 o'clock. It is in the south, and it's you can still get out and see Orion now that it's warming up. One of the most noticeable constellations is if you're learning constellations, this is the good first one to go for. And we got the famous red supergiant Betelgeuse, Rigel down here, the belt, and then if you got a telescope, I mean, one of the first things, you look at Jupiter and Saturn and the moon. Once you go past the solar system, the Orion Nebula should be one of the first things that you go for, and it's pretty easy to find. It's bright enough; it'll show up in binoculars or a finder scope on your telescope. In fact, Sunday night I just went out and took a picture of it, so maybe I'll show that. It won't look like this in a telescope, but this is a picture that I took Sunday night with that C-Star smart telescope, and I'm amazed that a 2-inch telescope can take a picture like this. And now this was not a snapshot. This was, I think this was over an hour's worth of pictures, but from my backyard using a light pollution filter. So this is a picture of the Orion Nebula, and this is a star-forming region. This bright area in here, there's new, fairly young stars giving off a lot of ultraviolet light, and that ultraviolet light is causing these gases to fluoresce. So the red is all from hydrogen. If you look at this in a telescope, oftentimes this region is what you see. You might not even see this other stuff. You'll see this bright region right in here, and it'll look green to the eye. This is emission from doubly ionized oxygen, which is kind of right in the green. So one of the few nebula where I notice color is bright enough to show that. So
Cool. Is there anything else notable in the night sky? I mean, of course there are, but
yeah. How long do you want to spend? But
yeah,
I think I'm going to stop with. I think I'm going to end soon.
Okay.
Because we do have other things to cover, but there's one more thing I have to cover, and that is next week we'll go to the 13th and find the moon, and there is a lunar eclipse next week. Now it's the night of the 13th, but mainly the morning of the 14th, so that's going to be Friday morning. And this is a lunar eclipse. Lunar eclipses happen at full moon, and we'll kind of go forward here. And now notice it got a little dimmer there. That's the penumbra. And then now we have the umbra. And so this is called the partial phase. About 1:30, we're going to hit totality. So I can make it exactly 1:30. So that's the main event. 1:30 in the morning, Friday morning. We have totality, but you have an hour, basically from 12:30 to 1:30, to watch the shadow go across it. The peak is at 2 a.m. and then it leaves about 2:30. And so 2:30 is about the end of it, and then you'll see the shadow start to leave. So you get an hour of it, the moon in the Earth's shadow. And for those who've seen this before, or if you haven't, you probably know that during a lunar eclipse, the moon will look very red. The last one we had, I think, was May of 2022. At least that was the last one I saw. That was total. We had a partial in there. And this is a picture I took with camera lens. So this is just a telephoto lens. So this is what it actually looks like. This is a little toward the end of totality, so one part of it's starting to brighten up. And it's red because the only light that's getting to it is the light that goes through the Earth's atmosphere. And just like the sunset, all the blue light gets scattered away. The red light makes it through, and so you're seeing that sunset red light going through our atmosphere, hitting the moon, and you get this nice red color. So during the partial phases, This is also from 2022. Your eye will be able to pick up kind of better, your eye seems to have better dynamic range than cameras. So you usually will be able to see, even when there's a bright part here, you'll see that there's kind of this dark red as it's coming over it. And so these are a couple partial phases from 2022. So the partial phases are difficult to take pictures of. Even the totality, you want a camera usually on a tripod. I think that picture I showed was a 1 second exposure. So the moon gets dark enough, you kind of have to have it timed. And it's kind of hard to hold the camera steady for 1 second. So usually want it on a tripod telephoto lens, and you don't have to do very long, but like 1 second exposures. It can be really tricky to get the partial phases. These are composites of these two pictures. And so these are what the pictures show up as. Basically, if you want the red color in the shadow, you overexpose the part that's not in the shadow. And if you don't want to overexpose, then it's just all dark. And it's disappointing because when you look at it with your eye, you do have this red color. And so you basically have to do two different exposures, and it is possible to combine them. And I actually just put up a little demo of how I do it. These are the two pictures in GIMP, which is a free software. You drop them in, move them around to line them up. And this is the overexposed one. This is the underexposed one. So you have them in layers. And just take that bright one and lower the opacity down. There we go. Usually about 25% or so. And you can kind of get the best of both worlds. You have to play around with it. And so that's basically how I made those pictures, to try and show both things, which your eye can see, but the cameras have a hard time doing. And so that's one way you can get a partial eclipse picture that kind of looks like, it still looks better. This is one of those things that looks better to your eye than it does in pictures, I think. Don't need a telescope. It can be fun with a low power telescope, but you can see it naked eye just fine. I like the view in binoculars. That's maybe my favorite view is binoculars, but a low power telescope is fun too. So, and maybe I'm assuming everyone knows what this is, but this is the Wikipedia picture. The sun is just casting a shadow on the moon. And this doesn't happen all the time because the moon's orbit is inclined a little bit. Here's my hand there. So inclined a little bit. And usually it passes over the shadow or under the shadow. Every once in a while it passes right through the shadow. And that's when we get the lunar eclipse. So unlike a solar eclipse, you don't have to travel as long as you're on the night side. So then you can see it. So
Right, so that was the shadow of the Earth on the moon.
right. Did I say the shadow of the moon?
No, you said the shadow of the
sun.
shadow.
Did I
of
say
the
the
moon,
shadow of the sun?
The shadow of the moon.
Oh, okay.
Shadow
Yeah.
of the Earth on the moon.
Yeah, shadow of the Earth cast on the moon.
Yeah. So the moon goes into the Earth's shadow.
Right. Yeah, moon goes into the Earth's shadow. If you were on the moon, you would see a solar eclipse. So the Earth would be blocking the sun.
And the Earth would be at new Earth phase.
Yeah,
Right.
right. The phases are always opposite
Yes.
Yeah.
for the Earth and the moon.
Cool. All right.
So
Very nice. And we did have a question there about Betelgeuse. So the time in which Betelgeuse will go supernova, and it is a massive star, so it will go supernova, will explode. That time is highly uncertain. So it could be tonight. If it is, please give us credit, this Cosmic Pod podcast, for forecasting
We're calling
that.
it.
Or it could be 10,000 years from now.
Right.
And that's the problem. We just don't know. We know it's less than 1 million probably, but we don't know the exact time.
Right.
And Betelgeuse is about 500 light years away, roughly. So even if it exploded like right now, it would take 500 years approximately for that signal to arrive here on Earth, that there's a sudden flash of light in the sky and Betelgeuse became extremely bright for a long period of time.
Right.
So
Believe me, we're looking for it. It's going to be a pretty spectacular sight be
I
honest.
I must admit, anytime I go outside at night and the constellation Orion is above the horizon, I do take a peek up towards Betelgeuse. You never know at that moment, and all of a sudden it goes,
Boom.
right? And it would be kind of cool to see. In fact,
So-
I would run in and report it, but I'm sure there's probably thousands of other people at that moment
Reporting
in
it.
time also looking
Yeah.
at it. But anyways.
So, yeah.
Okay, thank you, Dean, very
So-
much.
Yeah.
Yeah,
So-
and I will end because I think you're going to talk about it. This,
Yeah.
We're still waiting for this darn T
Yes.
Corona Borealis to go
let's,
nova.
let's save that, but we'll get to it. in a
We'll be
second.
talking about
And,
that in a moment.
Yeah.
Yeah.
So it is coming up in the spring sky. You got to wait until like 1 a.m. right now to see it.
That's right, exactly.
So-
Yeah.
All right. So,
Okay. So one of the things we'd like to update people on is what's going on, from our last update. And
right.
this is one thing we've talked about in the past, a couple different podcasts, is the Sphere X launch. It's been delayed again until March the 6th. So that's this Thursday. So that's currently scheduled for 9:09 p.m. Central Standard Time. But always in this kind of stuff, you never know when things get delayed. It can be weather, a
Right.
mechanical issue, or they're not quite ready to go. You just never know. So at least be on the lookout for the launch.
At least it's not going to Mars, so we don't have to wait 2 years if it does get scrubbed.
Yeah, so that way they don't have to rush and try to get it launched and to make the alignment
Right.
when they're not exactly 100% sure everything is ready to go, and you don't really want to do that.
Yep.
That could turn around and nip you in the wrong end. Now, the other update is, of course, on Saturday evening. If you're watching the news, we did have finally the landing of the Blue Ghost lander. So we reported that the last podcast that it had been launched. So it touched down, as Dean had mentioned earlier, in the Sea of Crises.
Mm-hmm.
You could use that description for a certain place around the world nowadays. You know,
Right,
so-
right. A lot of places
in other
the
words,
world.
did it land back on Earth?
Right.
You know.
A lot of places on Earth at the moment. But
Now, there's a few photos or images that were taken from the spacecraft, from the lander itself. And this one I like in particular. It's looking at the shadow of the lander. So you got proof it actually landed. It didn't go over on its side, which we've had in the recent
which we've
past.
had, right?
And the other neat thing is when you look off, you know, not that far above the horizon of the moon, you can see the planet Earth.
Okay.
So it's a beautiful, beautiful view. You know, this is kind of what you would see if you can vision that standing on the surface of the moon and looking back at the Earth.
Yep.
It looks fantastic. And as Dean had mentioned, the moon was just coming out of new moon phase when it landed. In fact, and if phases are opposite, that means the Earth should be nearly a full phase. And what do you see when you look at Earth?
Nearly a full phase.
Exactly.
Yeah.
So there's your proof if you want that.
Yep.
Now, Dean mentioned this object. This is T-Core Bohr. So it is a white dwarf that's accumulating material from its nearby companion star. And every roughly 80 years or so, that material lights up in nuclear fusion, and you get a sudden outbreak, increase in brightness of this object. Goes from about 10th magnitude to some people estimate it around 2nd magnitude or so. So that's about 8 magnitudes in brightness.
And
Now, each magnitude increase is about 2.5 times increase in brightness. 5 magnitudes is 100 times increase in brightness. So this is going to be well over 100 times increase in brightness when it does peak. Now, that peak, unfortunately, lasts for a very short period of time. So you're seeing, for the whole event, roughly a week or so. And so if this goes off, number one, hopefully it's clear often.
right.
I hate to see it at a time period where we have like 2 weeks of cloud cover,
2
right?
weeks of cloud cover, right?
Number two, we're hope that when it does go off, this object is placed well in the evening sky or the night sky so we can see it. I think the worst time was in November when it was close to the sun and we wouldn't have been able to see it because of that, at least for here on Earth, right?
Right.
Ground-based telescopes. But hopefully it's well placed. And it's, as Dean mentioned, it's coming up now in the very early evening. Or I should say very early morning. Early morning. And so at around probably just before it gets daylight, it'd be well placed above you to have a good view of it. Because
Right.
it would have been rising for several hours at that point, right? And it's only going to get better and better as it slowly drifts to the west over the course of every day
Right.
goes by. It was 4 minutes.
So we're back
west.
to being in a good position if and when it does happen.
Yeah, and there's no guarantee it's going to go this time either, right? That's
Right.
going to go this spring or this summer. And, maybe
Yep.
it'll be next year. These things are they're unpredictable to a degree.
Right.
We just go by what happened in the past. And in the past, you could put an average period on this of about 80 years or so. So we'll see how all that plays
Yeah.
out.
It's kind of like the sunspot cycle, which we say has an average of 11 years, but they can take up to 14 years for them to go around. So
Yeah, and there was a comment there from Fred about quantum entanglement. The one thing about quantum entanglement, and it's kind of a misnomer in some sense, is that, and even a NASA administrator had done this, not the current one because there really isn't, it's a temporary one, right?
right.
And not the recent one we had in the past. It was another NASA administrator. He said, oh, when people are on Mars walking around and exploring, we'll be able to use quantum entanglement to instantly communicate with them. And the answer is no, you cannot do that. Even a quantum entanglement, as far as we know today, you cannot send useful information from
Right.
one location to another, regardless of how far apart they are, instantaneously. That violates the special theory of relativity. So even quantum entanglement, you can't do that. So that's a little hook there. You have to always
Right.
worry about that.
Okay. So
Now, the next thing I want to share is this cool observation by the James Webb Space Telescope. And this is observations taken of what I call a rogue planet. That it's not a planet in orbit around a host star. It's one that is on its own.
right.
If you like, it's orbiting the center of the Milky Way.
Right.
Now, this particular object has a mass of about 13 times Jupiter's mass. So we think Jupiter, the giant of our solar system in terms of planets. This is 13 times that mass, right? And it's about 20 light years away. So it's pretty close, relatively speaking. And it takes about 2.4 hours to go around once.
Okay.
Okay.
And so, sorry, I misinterpreted a gesture I was getting. And so this planet is a rogue planet, as we term it. And the question starts becoming, how did it get there? So we don't know that. We think we've got a good idea that planets only form around stars. So this was probably a planet that was ejected from a stellar system. So in other words, it interacted with other planets in the system or with the star itself and got flung out. It was thrown out, that gravity assist business going on. Another possibility, though, is that it did form on its own out of one of these star-forming regions. So,
And the interesting thing about this planet that I find kind of cool is the atmosphere of the planet itself. And so as far as we can tell from the spectroscopy of the planet, that it has a layer of iron clouds.
right, which means, number one, it's pretty hot. Because, you've got to vaporize iron. I don't know what temperature that is, but I know molten iron is around 3,000 Fahrenheit, I think. So to get it now into vapor in the clouds, this is probably a fairly young object.
Yeah, very bizarre. And then above that, we have the silicate clouds, which is also bizarre when you think about that.
Yeah,
And then, so these light variation that we can measure with the James Webb Space Telescope are based on the composition of the atmosphere itself, that structure, as well as, the source of energy, the heat, in other words, from the planet itself, and what effect that has on the material of the atmospheres. Depending on the wavelength of light, some of that light would get absorbed by the iron, let's say, by the silicates in the cloud, or other light of different wavelengths would pass right through.
right. And that's how we get at the rotation speed. Well, how do we know that it's silicate and iron? And the answer to that is the spectrum. The spectrum always has, each element has a fingerprint of colors, of colored lines, we call them, that they give off. And when we split the light up and look at those colored lines that are produced, we can determine, hey, iron is here. And in fact, we can even determine what phase it is in, because even how it's combined chemically with other things is obvious in that spectrum.
And of course, that would tell us detailed information about the physical properties of the atmosphere itself.
Right.
From what you can see in the spectrum.
So,
Okay, and the other thing I wanted to mention, sort of the last story here today, is this paper that's been out for a few months now. So we've been kind of mulling this over a little bit. It is a published paper, as you see there. And if you just read the title, it's Supernovae Evidence for Fundamental Change to Cosmological Models. Another way to say this is a paper based on what we call the timescape cosmology.
Okay.
Now, the timescape cosmology, it's a little subtle, but here's how it works. Over the largest scale, so if you look at, let's start with very small scales like the size of our solar system. And if you're to wonder what was the mass distribution like in our own solar system, how was mass distributed? Well, over 99% of the mass of our solar system is in the sun.
Right.
Okay. Then the second body would be Jupiter, for example. Then you can go down that train, Saturn and so on. And so you would say that the mass is distributed highly and isotropically, as the fancy word to say it's not spread out evenly everywhere.
Right.
Okay. Now, if you increase your scale size, so if you zoomed out of the solar system, so you would see more of the surrounding neighboring stars like Alpha Centauri and so on and so forth, more and more of the mass appears to be spread out more evenly. There's less of these huge differences in density from one place to another. So as you increase that sense of scale, getting larger and larger and larger and larger, eventually you encompass essentially the observable universe itself.
Right.
And on those scales, mass is essentially distributed almost identically everywhere on average. We would describe that as the universe being isotropic and homogeneous. Isotropic would mean that everywhere I look in every different direction, it would look the same. Homogeneous would be if I were to move my location and move it significantly at some random location in the universe, it would look the same. That's what those two terms mean. Now, if you're trying to understand the evolution of our universe, we know that gravity is the major force that we have to deal with. And our modern form of that is, of course, the general theory of relativity. If we use the equations of general relativity and apply it to the universe as a whole, it's much simpler to calculate things, to solve the equation, if we assume this isotropy and this homogeneity, as we'd say, homogeneous and isotropic. That makes the equations easier to come to a concise answer. People have argued whether or not that assumption is valid. And one way you can see if it's valid or not is measure, not on small scales, measure over very, very large scales, cosmological distances, the structure, the large-scale distribution of the universe itself, how are galaxies distributed, all of these kind of things. And as far as we can tell with the very precise measurements, especially of the cosmic microwave background, this is the one way to think about the leftover heat from the Big Bang. The density fluctuations in that leftover heat are on the order of 1 in 30,000. So in other words, the universe is isotropic and homogeneous.
It's the same wherever you look.
To a level which is okay for the use of the general theory of relativity. Now, does that mean that there's no structure in our universe? No, not at all. If you go to smaller scales than cosmological, you do see structure. Galaxies are not distributed individually randomly through all of the universe. The structure includes, like they appear on the walls of bubbles. They're a filamentary-like structure. In the interior of those bubbles, it's relatively low density regions, roughly about 10% or so what we find outside of those bubbles. These are what we call giant voids today. So the overall appearance of the universe is like this frothy bubble-like mixture, which we call the cosmic web. Think of a three-dimensional cosmic web.
Mm-hmm.
Now, some people have argued that cosmology would actually change the way we view cosmology. If you look at the passage of time in different parts of the universe, and here's an example, we know that the presence of matter and energy curves space-time. It doesn't just curve space, it also affects time. So if you take a clock and you synchronize it with another clock, and you leave the first clock on top of an apartment building, and you take the other clock to the ground floor, hold them away from each other for a while, then bring them close together again, you'll find they're no longer synchronized. The clock that was closest to the Earth the longest runs slower compared to the one that was further away from the center of the Earth. It's well measured. We've done many, many experiments and in the last several decades, and we can measure that difference extremely well now using atomic clocks and other things as well that are used as clocks essentially. Now, the idea here is that in these underdense regions of the universe, in these voids, clocks then would run
Slower. Faster.
yeah.
Sorry, yeah.
They would run faster compared to a clock that was in a higher density region.
Right.
They would run slower because the time passage of that clock in the high density region is slowed down more due to the warpage of space-time, which is caused by all the matter and energy in that particular region of space.
Okay.
People have argued that these differences in time of these clocks that you have in the universe could be responsible for what today we interpret as dark energy.
Okay.
Now, dark energy, it was published in 1998. It was based on, at least the first research that was done on dark energy, based on these supernova type 1A explosions. They could use them as an independent way of measuring distances to the host galaxy. And then you compare those distances to what you get based on Hubble's law, the general expansion of the universe, in other words, redshift. And there was a discrepancy, and such that the supernovae were too dim.
Okay.
So they acted as if they were further away than what they actually are based on the expansion history of the universe. Now that gets really technical, but the problem is in here is how do you get two different measurements of distance when they should be essentially the same within the uncertainty? And one way to explain is we know that light falls off as 1 over the distance scale, but the expansion of the universe can be affected by something else, like the presence of some type of accelerated expansion, which causes the expansion of the universe to grow quicker and quicker and quicker with time and not slow down or stop, for example.
Right.
That difference then is what we call dark energy. That influence, that accelerated expansion of the universe is dark energy. Now, is it really energy? Nobody knows. We can just observe its consequences. But since its discovery in 1998, there have been several different methods that have been developed that are totally independent of supernovae observations that also point to an accelerated expansion of the universe. And that's what you're looking for.
That's what you're
Right?
looking
Confirmation.
for. You want different experiments that are pointing at the same result.
So what this paper, as well as this idea, it's sort of an offshoot of an idea that one particular person who's in New Zealand is living, has been pushing for the last couple decades now, is that these density fluctuations are strong enough that we can't disregard the change in the time evolution of different parts of the universe. But over very large scales, the density fluctuations in the universe and its matter is at a very, very low level. If you just use supernovae observation, which this paper is using, they basically say that essentially the standard cosmology with dark energy is almost as good as using this timescape type of idea. But if we refine and use part of our sample, then timescape wins over the standard cosmology. But the problem here is that we need other methods, not just supernovae, to look at this. Supernovae are very biased. They reside in certain areas of the universe in terms of density enhancements. They're not found in the voids of space per se. They're in where the galaxies are, which is along the filaments and along the walls of the bubbles in some sense. Mm-hmm. So they are a biased sample. What we have to do is include other ways of measuring this effect that are less biased, and then by having things that are totally independent of each other, then we could come to some consensus on this. But still, you can't get around the fact, and people have looked at this, it's nothing new really, people have looked at this idea and said that density enhancements, which are observable in the cosmic microwave background, those density enhancements are so low, it would have minimal effect on the presence of dark energy in our universe, that signature is still there, regardless if you try to use different clocks for different parts of the universe. That effect is too weak, too minor, and therefore the universe can be assumed to be isotropic and homogeneous, just like in standard cosmology.
So we've got a couple of questions. Basically, how does dark energy and dark matter affect the speed of light? And the answer is that they don't. This is why time dilation and curvature of space-time happen, is because the speed of light is constant, and regardless of observer. So the speed is staying the same, which means time has to be changing its rate. So
And so the other question is about the vacuum space. When we talk about voids, we mean voids that have a very low density of ordinary galaxies. Baryons, protons, electrons, neutrons, those kind of things as we lumped them all into. We're not talking about quantum field theory, where there's energy, that fields in the vacuum of space. Yeah, that's not the issue that we're talking about. The voids is what you actually observe directly, which is starlight.
right.
And that's what we're talking about here, these low density regions. But yeah, the whole vacuum of space, and that word, of course, is not really appropriate word. If you think the absolute absence of everything, that's not true. There could be this energy field that permeates through all of space that is directly related to the dark energy component of the universe, right? And there are, of course, fields, like I said, in quantum field, the electron has a field, the top quark has a field, the bottom quark has a field, the charm quark has a field, et cetera, et cetera, et cetera. So, yeah, that's...
Yeah, when you get down to the quantum world, things get really strange.
Yeah,
so,
there's no vacuum. I mean, we know that.
Right.
And that word was used back in even the Greeks' times, right?
Right.
So, but that's not the type of vacuum that we know and love today, if you want to think of it that way. But anyways, we're at the end of our podcast. That hour went extremely quickly. And just to remind people that we will not, and we had said this in our last podcast, we will not have a podcast next week. That is spring break for us. And there are some important things that we need to take care of on that Tuesday, so we will not be available to do the podcast. So our next podcast will be at Tuesday on March the 18th at 5 p.m. Central. And we've changed then, right?
It'll be daylight time.
Daylight time, exactly. 5 p.m. Central Daylight Time. If you're interested in this kind of stuff, if you're interested in STEM-related material, if you'd like to take courses on math or quantum field theory.
We've got several professors that can talk about that.
Yeah, you need to do higher level learning, right?
Right.
And so one of the things you could do, of course, is come to the University of North Dakota. We have lots of courses, not just in science, but other fields as well. And we need people from all walks of life.
Absolutely.
Everywhere.
We want different eyes on this problems. So,
well, who's going to communicate all our things to the public?
Right. So we need journalists and English people.
Just because you're a scientist don't mean you can write a book, for example, or doesn't mean you can adequately communicate your ideas to the layperson who's not involved in science and so on. So we need people from all over the place to help in this whole enterprise of learning. That's the thing. Now, we always leave you with a quote at the end of our podcast. Today I decided to read sort of an excerpt from Ethan Siegel, who published an article back in January on medium.com. And it's related to this timescape cosmology aspect.
Okay.
So I thought it was appropriate today. So I'm just going to go ahead and read it. Quote, I expect timescape cosmology to remain an area of interest for a few select researchers, but not to gain a broader following based on this research. It's exciting that a cosmological test has been concocted, but the truth is that dark energy's existence is now based on a wide, robust suite of evidence that's so comprehensive that even if we ignored all of the type 1a supernovae data entirely, we would still be compelled to conclude that dark matter exists. It's important to keep your mind open to new ideas, but to always let reality itself rein you back in. Like many new ideas, the timescape cosmology simply withers when faced with the full suite of cosmological evidence.
Right.
If you like this podcast, please give us a thumb up. If you subscribe, if you haven't already, and thank you very much.
Thank you for tuning in, folks. Have a good week, or a good couple of weeks.